Thanks for the invitation. I think I've mentioned a couple times, it's really nice to be in Santa Barbara, especially how cold it is where I'm coming from. So this is joint work I did with Jonah Kudler-Flamm and Sam Leuthäuser, who are both at Princeton. Sam is actually my office mate at Princeton. And well, I've also highlighted these two papers by Edward and collaborators just because this work is largely inspired by their recent work on this subject. And instead of citing them all over the place, I'm just going to cite them kind of up front. And the basic point of this talk is to explain this title. Okay? And the first thing we're going to focus on is the beginning part, which is the black hole. And so what I've depicted for you here is a black hole spacetime, or a portion of a black hole spacetime. And this black hole, this is very far after the collapse that occurred way far in the past, and this black hole is settled down to an essentially stationary spacetime. It's stationary because there's this stationary killing field that hugs, or that it goes null on the surface of this horizon here. And this black hole, you can, if you want to have a particular example in mind, you could be thinking of Sagittarius A star or something over here, and this is me in the exterior of Sagittarius A star giving my talk. Okay? And this time is now. And for all you could, if you don't like what I'm saying in this talk, or don't want to pay for my flight home, you could take me and throw me into the interior of the black hole, and this is the portion of the space-time that I would generally have access to. And despite my gesticulations or whatever, I will see an essentially stationary space-time. Okay? So for all intents and purposes, I could, for every measurement or whatever I see in this exterior and interior region, I could pretend that the space-time had been around forever. This is the more conventional diagram that you would have seen for a stationary space-time, meaning that this black hole I'm pretending has been around forever. If I take this killing field here, I can then extend it backwards, and at some point, it'll vanish at what we call this bifurcation surface. Here, it's a point on the diagram, but it's actually a two-sphere. Okay? So, all right, well, this black hole, rapidly settles down, or this black hole rapidly settles down to a stationary state. Any quantum state in the exterior of such a black hole will also rapidly settle down to a stationary quantum state on the algebra of any quantum field observables that I'm considering in the exterior of the black hole. This state is famously and necessarily mixed, at least during the duration for which I'm giving this talk, or you're going to throw me into the interior of the black hole, due to UV correlations across the horizon. So what do I mean by that? I have to really practice pointing it there. So what do I mean by that? Well, if I consider, for example, a massless scalar field, which we'll take as a concrete example for the rest of this talk, then if I look at the two-point function of such a massless scalar field across the horizon, the two-point function diverges in this state. It diverges in any such state, like 1 over the geodesic distance between the points across the horizon. Okay, so this point diverges, and what that really means is that the algebra of any quantum field in the exterior is in some sense strongly correlated with quantum fields in the interior of the black hole. And this degree of correlation gets stronger and stronger as I bring these points closer and closer together. Okay. So I mentioned this algebra of quantum fields. Well, what should you have in mind? Well, phi of x is really not an element of such an algebra. The reason for that really comes from this divergence I was telling you about before. You can't square this object due to the fact that it's, if I take the limit as x goes to x prime, I'll get this universal divergence. What you really should do is smear this object in space and time. If you smear it with some function f, which is averaging the field in space and time, such an object can be squared and is an element of the algebra that I was referring to before. Okay. And it is, well, there is a sense in which what I've just described for you is this space-time sphering is in some sense overkill. In the sense that, well, it really, I mean, if you just wanted to get an algebra element out of this procedure, what was noted as early as the 60s, at least in flat space-time and then generalized to arbitrary curved space-times, was that it's sufficient to smear the field just in time. And we'll see, I mean, the reason I'm pointing this out is because it's going to be so relevant to the rest of the story that I'm telling you later. So it's really just sufficient to smear this field in time if you wanted to get a well-defined algebra element. That's sufficient to regulate the field. Okay. Okay, so back to the quantum state that I was referring to before. Well, the quantum state is, of course, stationary. That's what I told you about before. But remarkably and famously, it is thermal at late times at null infinity. So if I go back to this diagram, the quantum state that I was referring to before, Hawking found it becomes asymptotically thermal at late times at Scri+, and that's, well, Hawking, after discovering this, knew something about black hole thermodynamics, and it directly implied to him that you should assign the black hole entropy to be the area of the black hole over 4G Newton. And therefore, the total entropy is the black hole entropy plus the von Neumann entropy of the quantum fields in the exterior of the black hole. Okay? So this is a very nice formula and really captures exactly, I mean, what we're learning from Hawking's original analysis. However, if you stare at that formula long enough, I claim you'll start to get confused. Well, the first thing is that both terms, Hawking's analysis is in the so-called semi-classical limit. So when I was telling you about these fields on the background, I'm not sure, okay, whatever. There we go. When I was telling you about these fields propagating on this curved spacetime, I was in this semi-classical limit where I wasn't allowing for, I was allowing for only negligible back reaction of the quantum fields, and I was in this G Newton goes to 0 limit. And this first term obviously diverges in this limit, and this von Neumann entropy, if I have a sharp horizon, the von Neumann entropy of the quantum fields in the exterior diverges due to those UV correlations that I was mentioning before. So both of these terms individually diverge, and that seems problematic for this formula. However, it was argued by Susskind and Uglum in the 90s that the sum of these terms can be renormalized in a manner that the sum might be better defined than their individual terms separately. Okay, so why am I giving you this talk? All of these citations are within the last century. And this, well, the reason is because remarkably, Edward and collaborators, well, they asked a different question. So they asked, well, what is the algebra of not the quantum fields that we were considering in the for the rest of the slide, but the algebra of gravitationally dressed observables. The point of this talk is to explain the highlighted phrase. And they asked, what is the von Neumann entropy of such observables? Okay? And the first remarkable thing, well, they were working specifically in Schwarzschild-AdS. We'll explain why that was important for what they were doing in a second. But in the exterior Schwarzschild-AdS, they found that the von Neumann entropy is now well-defined. That's the remarkable statement, given the fact that the von Neumann entropy of the original quantum fields was ill-defined. And not only is it well-defined, but in a suitable sense, it's equivalent to this generalized entropy that I was referring to before. Okay? So the point of this talk is to explain this and then extend this beyond the limited example of Schwarzschild-AdS. Okay? But let's explain the Schwarzschild-AdS case first. So, and this is the diagram of Schwarzschild-AdS. This looks very familiar or similar to the diagram I gave you before, except now instead of this asymptotic infinity that I had before, I have now the AdS boundary. Okay. Okay, and in AdS, the black hole is in thermal equilibrium. So what you I keep messing this up. The Hawking radiation now can bounce off this time-like boundary here, and you can set up the state such that not only is the stationary state stationary, but it's globally thermal in this exterior region outside the black hole. Okay? And, well, we're going to be considering constraints coming from gravity. And the key point that you should, well, keep in mind is that there already is a problem at the level of these quantum fields alone. So these quantum fields, phi of x or phi of f, are not diffeomorphism invariant. And the way we're going to ultimately construct observables that satisfy the diffeomorphism constraints are going to arise from constructing physical observables by gravitationally addressing these observables to either the boundary of my spacetime or another gravitating body. Okay? So phi of f, these observables on their own, they're not even time translation invariant, and they're generally not going to be diffeomorphism invariant. Okay, so how is this actually going to work? So if I take my field, my quantum field, and I treat it as a first order perturbation on my background geometry, then if it's a first order perturbation, it'll enter Einstein's equations at second order, because the stress energy tensor is products of my first order perturbation. And this will yield a second order perturbation then of the gravitational field. Okay? And this then we must quantize. Okay? This is a second order perturbation of the gravitational field that we must quantize. And we're just going to go ahead and do that. So what do I mean here? Well, if I look at in AdS, if I look at the total energy of my quantum fields on some Cauchy slice, so this is the integral of some stress energy tensor of the quantum fields, the delta here denotes the order and perturbation theory that I'm in. The total energy of my quantum fields, if I plug that into Einstein's equations, is, these quantum fields will now back react onto Einstein's equations and imply that the total energy is equal to the difference of the perturbed ADM masses of the left exterior and the right exterior. Okay? Okay, so what are these perturbed masses? These, I should have mentioned, let me back up if I can. Yeah, these perturbed masses are functions of the perturbed metric at second order. This is something I have not quantized up to now in this talk, and now I need to include these as extra modes of the gravitational field. Okay? And what do we mean by that? Well, the perturbed masses, the left mass and the right mass, generate asymptotic time translations of the left and right exteriors. Okay, so what I've bolded those symbols. That's meant to denote the fact that I want to now include them as quantum mechanical modes of the theory, and they satisfy. Well, I mean, this is the statement that they're generating these asymptotic time translations of the left and the right, respectively. And what I need to do is quantize these modes of the theory of this mode of the gravitational field. And since the perturbed mass can either go up or down, so its spectrum is valued in the real line, I can quantize this mode on L2 of R, which ultimately yields fluctuations of the black hole mass at order g nu. Why is it of the black hole mass? I'm quantizing this mode independent of the quantum field state. So here, in this formula here, this is being quantized, these modes of the gravitational field are being quantized independently, which means that regardless of what quantum field state I'm sending in, I also have intrinsic fluctuations of the geometry at order g nu. Which means that really what you're doing is you're allowing for, the only other thing that's gravitating in my spacetime is the black hole, and this is allowing for fluctuations of the black hole mass at order g nu. Okay, so what I'm really interested in is what is the algebra of observables in the exterior of a black hole. Okay? And when I consider that, well, this perturbed ADM mass of the left wedge lies in the commutant of the algebra of observables that I'm interested in, the algebra in the right wedge, for example. And therefore, this algebra of observables must commute with the mass that generates time translations in the left wedge. And therefore must commute with the sum of these two quantities, which is the generator of time translations of the quantum field plus the perturbed mass in the right. Okay? And the algebra of fields, so the quantum field alone does not commute with the sum of these two things because this thing generates time translations. But you can if you take the quantum field and conjugate it on either side in this manner, the joint observable, which is now the quantum field dressed to the mass, to the ADM mass of the right wedge, this thing commutes with this sum of these individual terms. Okay? Any questions about this? Okay, so yes?
Just to make sure, despite the fact that you're writing this as t minus tr, this tr is an operator.
Yeah. So I've written it suggestively in this manner. It's defined by the right-hand side, which is well defined. So I've written it suggestively. If you replace t as an operator by a c number, then this is exactly the expression you would get on the left-hand side. And so I've suggestively written it, and the colon equals means it's a definition, so you can't complain about it. you have to agree with it. But it's defined by the right-hand side. But it's very useful intuitively to think of it in this way. I'll explain why in a second. Okay, so this is a new algebra of observables. This is not the original quantum field algebra. These are now quantum fields dressed to the asymptotic boundary in a manner that satisfies the constraints. Okay? So now, what is this algebra? That's what this slide is doing. So to really precisely tell you what this algebra is and whether or not, well, what the new entanglement structure of such a theory is, it's useful to go back, almost a century ago, to Murray and von Neumann's classification of such algebra. So whenever you hand me an algebra, it's classified in these different ways, which I'll review now. And so they had three different types of algebras. The first one, which I'll refer to as type 3, these are very familiar to you. These are just local quantum field theory. We encounter this just in the exterior of a black hole. Okay? In this case, because of the high degree of correlation of quantum fields across any local region of the spacetime, such algebras don't admit any pure states, but due to the UV entanglement across any boundary, the algebra does not admit any density matrices either. Okay?
Can you say a bit more about what it means to not admit a pure state?
Not admit a pure state is that every operator is entangled with another operator in the exterior. So,
if I write down a free field theory, I would say the ground state is a pure state.
That's a global statement about a global quantum field theory, not a statement about local quantum field theory.
The ground statement is the statement within local. I'm not sure what you mean by local quantum field theory.
Local quantum field theory would be the quantum field theory described in just this room, not a complete Cauchy surface.
He means a pure state for, say, one particular region, right? So if you're one particular region and you want a pure state for that, you could try to write down something that's factorized, but then you know that has infinite energy. So that's infinitely far.
You can engineer pure states, but then they'll have infinite energy across the boundary in which yeah, that's correct. You have to basically break the entanglement that I was referring to, even on the horizon of the black hole. Okay, but the one that you, I think, were, or I was referring to was the type 1 case. That's the case, well, that's the case we normally think about. That's the case where it admits pure states and also density matrices. This is what happens when you just consider quantum field theory on a complete Cauchy slice. Okay? So the intermediate case, which is intermediate in number but also in its quality, is the case where of type 2, these situations, or these algebras, don't admit pure states still. But, so every operator is still, in some sense, correlated with an operator in the kind of exterior region I'm considering. But density matrices and entropy can be defined up to an overall state-independent constant, which will appear in all of the formulas that I'll be writing. Some terminology: if there exists a maximum entropy state, the algebra is called type 1. So entropy is now well defined, so I can ask whether there exists a maximum. If there exists a maximum, I call it type 1. If there doesn't exist a maximum entropy state, we call the algebra type 2 infinity. Sorry, type 2 1 and type 2 infinity. Okay. And so what's an example of a type 2 algebra? Well, I claim the algebra of the dressed observables that we just constructed in the previous slide is an example. The more precise statement is that if the state that we're considering in some region is thermal with respect to the diffeomorphism that we were deciding to gauge, then the algebra that we just constructed is a type 2 algebra. Okay. So this is the example of a type 2 algebra, which was shown by Takasaki in '73. Okay, so well, entropy, I claim then, is, so this algebra that we got from just following our nose with Einstein's equations is a type 2 algebra. The entropy is therefore well defined, and we can, well, ask what the entropy is of any given state that we're interested in. And one such state is what I've written here, where, you know, it's the state of the, any state now is the state of the quantum field, now together with a wave function on this extra gravitational mode that I've added. Okay? And what is really physically going on? Why are entropies now better defined? Well, the wave function, which I've written the Fourier transform of the wave function, specifically with respect to this time that we added in, regulates the quantum field in precisely the manner that I was describing on the previous, on the first slide. So if I can go back, sorry, here. So I suggestively wrote it in this fashion, as was mentioned before. When you now take expectation values in a state, you have to choose a wave function with respect to this extra mode. And that effectively averages your quantum field in this extra mode. And the result by Borchers and others suggests that now this new intrinsically quantum gravitational observable is basically intrinsically regulated by the extra mode of the gravitational field. Okay. Sorry, there's quite a lag. Here we go.
Question. Is omega in the theorem already a pure state?
No. So omega is I'm in this region R, in the exterior of the black hole. So it cannot be pure because of.
R does not allow us a pure state.
Omega is not pure.
Oh, okay. You do not assume omega is pure. Okay.
Yeah.
I see.
It's thermal, so it cannot be.
Okay.
Okay, so and in particular, now if you take a, Edward considered a semi-classical state, so if I'm averaging these quantum fields in time, many of these states are going to look nothing like the original quantum field states that we considered before. The correlation functions of my quantum fields will look nothing like the original quantum fields we considered before, unless this f function is sharply peaked in time. Then we're not averaging the quantum fields by very much, and then the quantum fields look very much like what Hawking was considering in his original analysis. These are the so-called semi-classical states. And indeed, the von Neumann entropy of such semi-classical states, what was found, is equal to the generalized entropy up to this, what I call a fluctuation entropy term. If f was a Gaussian with some width, this is roughly proportional to the width of the Gaussian. Yes? This is just the Hilbert space.
Yeah, which tensor product is that?
This is, sorry, it's the quantum, this is an algebra on this Hilbert space. This Hilbert space is the Hilbert space of the quantum fields, tensor this extra gravitational mode.
Okay.
Is that clear? Okay. Oh, and finally, this algebra is type 2 infinity, which should be intuitively obvious because the area of the black hole is not bounded from above. Okay? So the entropy can be increased. Okay, so now let's consider the other case that Edward considered, which was the case of de Sitter spacetime. So this is the only example that will not contain a black hole in my talk. And the diagram looks very similar to the case we considered before of AdS, but it's completely different. Well, the first thing is that now the asymptotic boundaries are space-like into the future, and this space-time is closed. Okay? And this region R now is the domain of communication of some observer, this inertial observer that I've highlighted that just lives forever in the space-time. Okay, and well, one only similarity between the keys we considered previously and this one is that this spacetime admits a stationary state as well, the so-called Bunch-Davies state, which, when restricted to the right wedge, is a thermal state. Okay? So, but this is the key difference. Well, de Sitter spacetime is a closed universe. And so Einstein's equations, just as before, will say that the total energy of the quantum fields will be equal to the difference of some boundary terms, but in a universe without any boundary, this is just going to be 0, or any favorite number that you wish to pick. And this, therefore, yields a trivial algebra, because this constraint is really going to say that all of my physical observables must commute with this with the generator of time translations, and there's no local observable that's time translation invariant except for the identity. Okay, so just as I mentioned before, in order to obtain a non-trivial algebra, one must dress the field to a gravitating body. And in order to avoid any complications of adding a very complicated extra field or degree of freedom, Edward just considered, adding a simple, extremely simple object. It's just a clock with some energy, and conjugate time tau, and the Hilbert space of this clock is valued again in L2 of R. Okay, this is the energy spectrum of this quantum field, of this clock. Okay, and so this is just basically engineered to basically break the degeneracy of this constraint. Okay, so now my new constraint is that the total energy of the quantum fields, together with the energy of this extra degree of freedom, this clock, must now commute with all my observables in the right wedge. Okay, and the algebra of these dressed observables, the ones that commute with the sum of the energy of the quantum fields together with the energy of this clock, is exactly as I showed you before, where now this time that we had before is now replaced with the time of the clock. Okay? And now, as opposed to having a black hole in the background of the space-time, we now added by hand this observer, this extra degree of freedom, and it's reasonable to impose that the observer energy that I added be bounded from below. So therefore, we should project the observer's energy to be positive onto this algebra that we've constructed here, generated by these fields. Okay? And well, if the observer's energy is positive, if you put energy into the space-time, the cosmological horizon must shrink. Therefore, if the energy of the observer is positive, the area is then bounded from above, and therefore the algebra is type 2-1 in this case. And the entropy, again, of any semi-classical state on this algebra is again the generalized entropy up to this fluctuation term. Okay, so now let's do an example that was not previously considered. And this is the case of an asymptotically flat spacetime. So this is a diagram that I presented to you previously. And this black hole now is radiating into empty space. And so therefore, the state is thermal at asymptotically late times at Scri, but is not globally thermal in the right wedge. Okay? So this is the key difference from before. And Einstein's equations, well, I mean, so regardless of that key difference from the previous considerations, we can still follow our nose, we can still do everything just as before, and I mean, nothing should really change that much, hopefully. So Einstein's equations, again, relates the energy of the quantum fields on any Cauchy surface to the perturbed area of the black hole, as well as the ADM mass. Okay, so if I take a Cauchy surface for this space-time and I integrate the energy of the quantum fields, that's what's denoted by the right-hand side expression of this formula. Okay, and that's going to again be equal to the difference of two boundary terms, one being the perturbed ADM mass at spatial infinity, and the other being this perturbed charge all the way in the far future. This charge is effectively the perturbed area. Well, if I took it at any finite time along this past horizon here, this perturbed charge at some affine time u is the perturbed area up to this expansion term. Well, and if the black hole settles down, then the perturbed charge will just be the perturbed area in the asymptotic future. Okay? So that's the formula that I have here. This guy lives in the commutant of the algebra that I'm interested in, so this is going to generate for me the exact kind of constraints that is referred to before. Okay, so if we quantize again the perturbed ADMS at infinity, then on this which can again go up and down, so therefore we quantize it on this L2 of R space, the algebra of the dressed observables in the exterior of the black hole is again given by the same expression that I gave you before. Go ahead. Yeah.
So this charge that you have off on the
yeah.
that's constant? No, it's
No.
changing. What, could you just choose not to quantize it or not to?
No, you do quantize it. Sorry, I'm now skipping well, you quantize both, but this guy lives in the commutant of the observable. So now just move this guy to the right side. Now you get the same constraint as before, which is the ADM mass plus the generator of time translations must commute with all observables in the right way. So I skipped a step. I apologize. But you should quantize both. All charges should be quantized.
Sorry, and it's important that you actually go through the horizon to that other point. You can't stop at the horizon.
Yes, you can't. Well, you can't stop at the horizon because this Hamiltonian, if you just cut it off here, its expected value is well defined, but its correlation functions are divergent. So in order to get a well-defined gravitational constraint, you need a complete Cauchy surface for the spacetime. This is not an operator if you just stop at a finite place. Okay. Okay. So barring the step I just skipped, the algebra of the dressed observables in the exterior of the black hole should look now. You're all experts at this point. It's exactly the same as I gave you before. Okay. However, the black hole is not in equilibrium, and one cannot directly determine the type of this algebra just by staring or using any of the previous theorems that I showed you before. Okay, but to determine the type, it's useful to go back to the quantum fields, these 5 x's that I had before, and re-express them in terms of initial data. Okay? That sounds like a mysterious idea, but just hang on for a second. So what do I mean by that? Well, if I take any observable of the algebra, so let's say phi averaged in some region like here, I can use the equations of motion and propagate it back to the asymptotic boundary. Okay? And what you can prove is that the algebra of observables in this exterior region factorize into an algebra of observables living on the past horizon and an algebra of observables at infinity. And if it's a massless field, it's an algebra of observables living at scri. Why is this a non-trivial statement? Well, there are null geodesics that just circle the black hole forever and never hit the past horizon or scri. But you need to show that these are, that there's enough dispersion and decay in such a manner that there's nothing really living on this photon sphere at asymptotically early times. Okay? But with this result, you can now learn this result and the following, which is that not only does the algebra factorize, well, obviously all the states do then, or not, this state does, and you can, if you pull this state back to infinity, well, the state at scri minus is exactly, well, first of all, it's pure when you pull it back to past null infinity, and it's equal to the vacuum state that you would have just sent in from past infinity. This is effectively Minkowski spacetime out here. However, go ahead.
This factorization, does it happen in any dimension?
Yes. That was shown by Jonathan Luke, Stanford. Oh, its result, if you take his paper and then you, yes, the answer is yes. However, this state, when you pull it back to the past horizon, is thermal, exactly thermal on this past horizon. Indeed, it must be thermal because when you propagate this state to the future, the thermality that from the past horizon here is what ultimately becomes the Hawking radiation that you get at asymptotically late times at scry. Okay, go ahead.
The fact that the state is a vacuum at scry minus,
Yeah.
you said that was basically a consequence, but isn't that an input? I mean, couldn't I have considered the state at late time, which corresponded to sending in particles?
Omega is a stationary state. It was defined as a stationary state. Every other excitation above it will not be vacuum here if you decide to send some laser beam or something here, but that'll be in the Hilbert space above the vacuum. Okay. But the fact that it's a stationary state also directly implies that it will be thermal on the past horizon. And in some sense, it's thermal because of the presence of the black hole. These modes will be ultimately what become the Hawking modes at future null infinity. Okay, so now we're in business. It directly follows that when you take this algebra of dressed observables, which I must have some here, the algebra of dressed observables, and pull it back to the past horizon, Takasaki's theorem tells me that the algebra of observables, because the state is thermal on the past horizon, this algebra is type 2 infinity. And the algebra of observables at scry, well, prior to dressing, the vacuum state is a pure state. So the algebra of observables prior to dressing is type 1, and after dressing, further dressing doesn't change the algebra type. And so what we get is that the algebra of observables at scry, it had pure states before, it still has pure states, it is still type 1, and the full algebra is the tensor product of these two algebras, of these two dressed algebras. And then the full algebra, therefore, is type 2 infinity. And the von Neumann entropy, can I just finish? The von Neumann entropy of any semi-classical state is, again, one finds equal to the generalized entropy up to these fluctuations. Go ahead.
Yeah, what is type 1 sub-infinity?
I didn't explain the infinity part. Basically, quantum field theory on any Cauchy slice is type 1 infinity. The type 1 integer number just refers to like the tensor product of some qubits. And some sequence of an infinite number of such qubits, one could obtain type 1 infinity. But type 1 infinity is basically quantum field theory on a complete Cauchy slice, is what you should think of. That's basically it. Okay, good. All right, and then in the last 10 minutes or so, let me just finish with the final example, which is Schwarzschild-AdS. So I should have mentioned the previous example was an asymptotically flat Schwarzschild, but in the paper we do Kerr, you could have done Kerr-Neumann. I basically explained to you all the essential details. And in this case, we're going to do Schwarzschild-AdS, but you could do Kerr-Neumann-AdS if you wanted to, in exactly the same kind of generality that I will just now describe. So there again exists a stationary state in this region, but of course it can't be thermal. I have two horizons here now, each one with a different temperature. The black hole, generically, the black hole will have temperature, inverse temperature beta 1. The cosmological horizon will have inverse temperature beta 2, and these need not be equal. And so therefore, the omega, the stationary state that I've been referring to in this talk, need not be thermal in this region, but it will be thermal when pulled back to the past horizon here and scry. And again, indeed, the factorization of these algebras can also be similarly proven. Okay, so what's the key difference? There is one key difference. Well, as opposed to the previously considered cases, what we'll find is that both boundary charges that we're going to get from Einstein's equations lie in the commutant of the region that I'm interested in. Okay, so the gravitational constraints will again yield a trivial algebra. If I look at this integral, if I integrate the energy flux on this Cauchy surface, I'm going to get two perturbed charges, both lying in the commutant of this algebra of this region that I'm interested in. And so what the constraint is again going to be that I must commute with the generator of time translations in the bulk of the spacetime. Okay? And so that we're just in the same danger as in the case of de Sitter spacetime of having a trivial algebra. And the way to break this degeneracy is again to add an extra gravitating body, just as before. Okay? So it would appear then that the gravitational constraints that we're getting are identical to the case of the de Sitter case. However, there is an important key difference, which is that we have both a black hole horizon and a cosmological horizon, and those can independently fluctuate. And what I'll show you on the next slide is that that actually yields stronger constraints on the algebra than the global one that I just showed you. Okay? So the way to see that is to basically split up. Let me go back. You get one constraint. I just wrote down one formula coming from this one Cauchy surface here. Let's pull this Cauchy surface back to the asymptotic boundary and split it up into the contribution of three contributions. One coming from the black hole, one coming from the cosmological horizon, and one coming from infinity, past I minus.
But you need to impose that the temperature has to be the same.
No.
No, not at this point.
Never.
Never. Okay.
No. If the temperature is the same, that would make my life a lot easier, because then it would be thermal in this region. And but no, I wouldn't want to do that because I'd like to be a bit more general. Okay, so that's what I've done here. This is the Hamiltonian. This is the generator of time translations just on this past horizon here, of killing translations here. This HC here is the generator of time translations here. They individually satisfy, well, it can be, this Hamiltonian on the past horizon here can be written as the difference of boundary charges, one living in the far future here and one living in the asymptotic past. This Hamiltonian here, living on this black hole horizon, can be written as the difference of boundary charges, one living in the far future and one living in the asymptotic past. And the sum of these two, so the incoming observer borrows some area from either the black hole horizon or from the cosmological horizon, and that's what this formula in the asymptotic. So if you add these three up together, you get the total formula that I gave you before. Okay? But note now, if I just forget the rest of this diagram, just look right here. If I look at the algebra of observables living here, they must separately commute with this charge living here. Right? The algebra of observables living on the past horizon must commute with the charge living here. This algebra of observables living here must separately commute with this charge living up here. And that's what I mean by it imposes stronger constraints. This imposes a separate constraint. Each killing horizon imposes a separate constraint on the algebra, one coming from this past horizon and one coming from that. Okay, so if we quantize the area of the black hole horizon and quantize the area of the cosmological horizon, the constraints imply that the algebra of dressed observables just on the past horizon of the black hole is type 2 infinity. So I'm asking, let's go back. Let's go back. I'm asking, look at the observables living here. What are the ones that commute with the sum, with the charge, this Q plus? Well, that's the one that commute with its generator of time translations plus the perturbed charge that I've quantized. Okay? So that algebra alone is type 2 infinity. The one that I get from the past horizon of the cosmological horizon is also the type 2 infinity. And the full algebra is the tensor product of these two individual ones. Okay? And then again, it's physically reasonable, because I put this guy in by hand, to impose that the energy of the observer is positive, which means that the sum of these two must be bounded from above. But if the sum of the two are bounded from above, that means the difference of the areas is an unbounded mode. And the algebra of the dressed observables is what you find is type 2 infinity again. Because you have now an unbounded mode of this charge. And the von Neumann entropy one finds of any semi-classical state is again the generalized entropy plus a fluctuation term. So let me just conclude with the general. So I've tried to present things in a manner that it's obvious how to generalize this to any spacetime with any killing horizon, but this slide is meant to do that. So let me just quickly say and reinforce the point again. The algebra of any observable in the exterior of any killing horizon which admits a stationary state, which I hope should be clear if you have a black hole formed from collapse, then this state is generally not thermal in the exterior of this horizon, but it is always thermal on the past horizon. So there is a thermal character of this state that always exists, and using this result together with Takasaki's theorem, you just find that the algebra, well, I'm restating statements that I've already made multiple times in the talk, but now it's in blue. So the algebra of observables is generated from the past horizon is type 2 infinity, and it's basically, well, if the spectrum of this perturbed area is unbounded, and if the spectrum is bounded due to global constraints, then the algebra is type 1, and there exists a maximum entropy state. If the algebra also factorizes, which is the case for free theories and believable for theories that are weakly coupled in the IR, however, I should say the state of the art of what is known about, for example, stationary states in general interacting quantum field theories is very minimal. So the strongest statements I can make at the moment are for free theories and theories that are weakly coupled in the IR. And in those cases, the algebras will factorize, and when they do factorize, and sigma prime, this other piece of the Cauchy surface, is either another killing horizon or infinity, then the algebra will be type 2. And the von Neumann entropy of any semi-classical state from these considerations will always be the generalized entropy up to a fluctuation term. If the space-time contains a black hole, then the entropy is always going to be unbounded, and the algebra will be type 2 infinity. So let me just conclude because...
Sorry, can you just read that one more time? I'm trying to understand the if the algebra factorizes.
Yeah, yeah.
Then you get...
Yeah, so then if the algebra factorizes and this surface here is either another killing horizon or infinity. If it's infinity, then this algebra is type 1. If it's another killing horizon, just like in the Schwarzschild-AdS case, it'll be type 2.
In the full algebra
Yeah. Yes. And the von Neumann entropy of any semi-classical state will always be... Yes, go ahead.
I'm sorry, could you remind me what the second term on the right is?
Yeah. So this is a fluctuation entropy term. It basically it's the... if f is a Gaussian, it roughly corresponds to the width of the Gaussian. It's proportional to the width. It's a term that appeared even in Edwards' original work. They were able to identify it with the logarithmic correction to the entropy, but I can't, off the top of my head, remember why how they were able to identify it. It is
small in some sense.
It depends on the choice of f.
It depends on the choice of f.
Okay, but I don't want f to be too wide because then I'm smearing over way too long. And
I think.
small when f is narrow.
Yeah, I think it is small when f is narrow.
You can't make it vanish.
Can't make it vanish, no.
So it depends on what.
Depends on f. F can't be a delta function, otherwise it's not L2. So f has to have some width.
But can I make it arbitrarily small?
Yeah, I think so. Yeah. But it's for completeness, I've added it in. Yeah.
And C is?
C is the overall state-independent constant that so this algebra is type 2. The type 2 case is basically entropy is well defined up to a state-independent constant.
You get to pick, or you give?
It just means
It's just meaningless. It just means that this it's not defined. That means that entropy differences are. Yeah, and I think in a recent paper by Edward, he just said let's just choose it to be 0. so I don't know. I'll leave it up to you to define it. But for completeness, I added all the terms that contribute to the relevant expression. Okay, there was nothing important about me being in 4 space-time dimensions, or in particular working with Einstein gravity. If you change either of those things, well, the entropy in higher dimensions, the story basically follows in complete with no change. The only change that happens when you change the theory of gravity is that the black hole entropy is going to now be replaced in the generalized entropy expression by the walled entropy. because again, we're considering a stationary black hole. I gauged the generators of time translations, but there are other isometries of the black hole, of a general black hole spacetime arising from compact, some rotational isometries and so forth. These do not change the type of the algebra, and don't change any of the relevant expressions that I gave you today. And an analogous construction I just showed for scalar field, I mean, obviously will hold for any other free fields in the theory, and I believe also for any theories, any situations in which the previous slide holds. And just to conclude, the basic point is that the generalized black hole entropy for any black hole in the context that I've just described today is the von Neumann entropy of the algebra of physical gravitationally dressed observables. That's the basic idea. More generally, these results, I think, suggest a very deep connection between, and I would strongly say unexpected, at least to me, connection between the physical observables of quantum gravity, the ones that obey the gravitational constraints, and the generalized black hole entropy. And I think it would be really interesting to explore those connections further. Let me end there.
So in the case of de Sitter space,
Yeah.
you don't have a boundary. You would have to introduce this observer.
Yes.
So what does that mean? And shouldn't the theory produce its own observers?
Should the theory produce its own observers?
Where
yeah.
is it? Let's
Well-
say we actually live in de Sitter space.
Well, I would say that the theory producing its own observers would mean that you can dress the fields to some feature of the spacetime, right? So the cosmological horizon or something. I think when the fact that it's a closed universe means that you need some other degree of freedom around in order to have a non-trivial gravitational constraint. I mean, I guess Don was that.
Rephrase the question in a more technical way,
Yeah.
which is there was the comment about that point in the talk that because you needed the operators to commute with H,
Yeah.
if you didn't add anything, the only operator that commuted with H was the identity.
Yeah.
That technical comment confuses me. Is that really true? Is it a theorem?
The algebra is generated by the local field the local fields. The local fields are, 5x. You can smear it if you want, but 5x is not time translation invariant.
It's not. But suppose I have 3 flavors of scalar field. Doesn't the total Hamiltonian commute with the Hamiltonian for each field separately?
3 flavors of what?
Scalar field.
Non-interact.
Not interacting, just linear, just for simplicity. Not interacting linear.
Why?
Indirect rotation.
Not this approximation.
But the 3 flavors of scalar field. Sorry, and you want what do you want to commute? Maybe
So there's a total Hamiltonian.
Yeah, the total
that
Hamiltonian.
we want to commute with.
It generates time translations of each of your fields separately. Yeah.
But suppose I just consider the Hamiltonian for each field separately.
Yeah.
Aren't those conserved quantities that commute with the total Hamiltonian? Why aren't those examples or counterexamples of the statement that the only operator that commutes with the total Hamiltonian is the identity?
Yeah. Okay. So I agree. So certain other in the theory that I was considering, the statement is true, which is just the single field alone. If you add other degrees of freedom, the Hamiltonians of those guys will commute. But that's not going to change the fact that the gravitational constraints will tell you that the sum of all of the Hamiltonians of all 3 of your fields must add up to 0.
That's
right?
true.
So that's the key problem.
My objection,
yeah.
related to David's question, is if I have a general theory, I might think that there exist things you might call appropriately relational observables, which are things that commute with the total Hamiltonian, which in some sense are like saying I could build an observer out of the fields that actually live. Now, there are various technicalities discussing various cases, okay? But I'm trying to understand, and it's actually true that there are technicalities to discuss. I'm not certain that you can really do this in a
I think the space-time under consideration has too much symmetry. Because, I mean, so for example, there's long discussion of how, I mean, we were discussing earlier today, right? If you have a space-time with not a lot of symmetry, you can take the different, curvature scalars, and you can use those as, effectively fields of your space-time, and then you could take, use them as, their level sets are now some coordinate fields on your space-time, and you can now say phi of x, that's not what I mean phi of those 4 independent fields, those 4 independent curvature scalars. I don't know how to do that for a case where the space-time has so much symmetry, where I don't have, those, yeah, so that's...
I would have thought you could do it in this context where you're only worried about one time translation. But I'm trying to understand, to what extent is it a theorem that the only thing that can use with H is the identity, and what context is that true?
It's true in the context I stated it, but which is the single field that I was working with.
Single free scalar.
A single, yeah. I won't try to generalize it beyond that. It just meant that I already, in that limited context, I ran into a problem, and I need to solve it.
Does that commute with H?
It does, but it needs to enter the gravitational constraints non-trivially for this generator, right? So like you need, it's not just enough to consider an object that commutes with H. You need to consider it, the spirit. Sorry.
The only thing that commutes with H was the identity.
Okay.
That's what I'm objecting.
Yeah. Okay.
I'm not saying you can use it.
Yeah. No. I think I'm going to have to walk back the statement. So I agree with the general feeling that there are the things that commute with the generator of time translations. I'm not going to object to that. I'm saying that those are not going to be useful in this regard, though you need something that gravitates, that breaks the degeneracy of that gravity is imposing on it, right? So you need to put something else in that gravitates in order to break that degeneracy, and the simplest model is to just put in some clock or whatever that breaks that degeneracy. But I think a more sophisticated model, I think, would be, it would be better to consider other models. I'm not so happy with the observer in that scenario. Just something to break the degeneracy is, I think, what you need. Go ahead.
Just to follow up Don's comment, what if we restrict to local observers, that's the local operators, and all the only local operators, there's no local operator that commutes with the Hamiltonian?
Yeah, so that was the spirit of the comment, but I didn't say local in the statement, so I walked back the statement that I wrote, I think. But yes, if you restrict to local operators, then you will run into this problem.
I guess
What you've done, you're imagining that one could construct observer.
Yeah. One can construct, I believe one can construct observers from the fields that are there. How?
Yeah.
You can take, say, another scalar field and put it in a specific state that's time evolving. Okay, so that gives you something, with some time evolution that then your other fields can evolve with respect to.
You just have to something that acts like a clock.
So you would object to the clock, but you would be okay with adding a scalar?
I'm just saying, I think that you can, in some sense, drive this artificial observer as a limit, at least, of things you could do with actual fields that are...
Yes, this I find plausible and I agree with, yes.
A limit in what sense? With many degrees of freedom?
Well, you want to have good clocks, right?
Yeah.
You want to have good clocks.
Okay, but what's the parameter?
The parameter
Things like
is
mass is one. You want...
you basically need the WKB approximation. So you want to get something which acts like it has a Hamiltonian which is linear in momentum. And that's something that naively any decent field has a Hamiltonian which is like quadratic in momentum. But in the WKB approximation, you ignore that second derivative term of the Schrodinger equation, and in fact you can think of it as
But that typically is a semi-classical limit or something.
Yeah, it's a semi-classical.
So it's a large number of degrees of freedom or something.
I guess you want something bound up.
State or what?
That's correct. Something like that. It could be any of the above. I mean, a nice example is to, as Steve said, use some other scalar field as a clock, and to make it into a clock by choosing some highly excited coherent state of Clarke. There's an example. But something that gives you, as you say, some semi-classical engineering. Now, it's an interesting question. If you back away from that limit, and you use a less perfect clock, is the algebra still type 2 1 or type 2 infinity? It's not obvious that an imperfect clock gives you a worse algebra. Okay. But yes, to reproduce this exact thing, you need to take something like a semi-classical limit.
Yeah, I would say just from the kind of simple Borchers type arguments, which seem to be much more robust than any of the other things I was referring to, the imposing the diffeomorphism constraints associated to time translations should give you better regulated observables. And that alone should be good enough. My conjecture is that that should be what's driving all of this.
I mean, a simple concrete model would be to use something like their observer, but instead of saying that that there's a Hamiltonian and it's conjugate to a time, treat it like a free particle Hamiltonian. A piece where it's conjugate to an x, and then you get the WKB limit, you can reproduce this, then you can check the rigorous theorem of is the algebra still type 2 or type 2, and I predict that quantum field theory will be basically equivalent to that as far as this time translation is concerned. So that's to consider isometries.
Yeah, so your first statement that in a general theory of gravity, it all goes through and you just get that area term replaced by the wall, is that just follow from the fact that you're using a Hamiltonian constraint and wall basically derived is generalized entropy by looking at that?
Essentially, yes. I mean, what's entering would, I mean, yes is the short answer. Do you want a longer answer? What's basically entering is this Q here. This Q I defined as an object that's conjugate to the killing isometry. Bob basically derived this charge as the conjugate to the killing isometry. So what enters, basically what ends up entering into the generalized entropy formula that was here at some point, is, the area term ends up being what this charge is.
So Bob never went to this other
that's
region,
right?
He worked on the horizon.
Right, so this,
But you're saying it doesn't matter.
That doesn't matter. Well, it ends up being this charge evaluated at the bifurcation surface. That's the important thing. So I was saying more generally what enters is this conjugate to the killing isometry, but when you calculate what the generalized entropy is, you find that it's whatever the charge is evaluated at the bifurcation surface. So, and Bob derived that. It's the wall of entropy.
Can you say something about the non-stationary case and how to possibly generalize it?
Yeah. So let me think of this is fine. Forget the rest of this, just we can consider it. So there's one case is kind of, so I derived effectively the generalized entropy for this entire exterior subregion. By non-stationary, you could mean one of a few different things. One is that I have perturbations of a background geometry that's stationary, but I'm considering other horizon cuts as opposed to like a dynamical black hole entropy type scenario. Is that what you're referring to, or are you referring to just not having the isometry in the background?
Any way of not having isometry.
Yeah, so even the horizon cuts kind of kills the isometry in the sense that this killing field here doesn't preserve a horizon cut. So if I look at a subregion of the spacetime that isn't the entire exterior, in some sense I should be gauging all the diffeomorphisms associated to the subregion of the spacetime, which means that I now can't gauge the background isometry anymore. I should gauge something else, the diffeomorphisms that preserve this subregion. So one can do this. Again, you can repeat the same story that I just was giving before for diffeomorphisms that preserve this subregion. They're not isometries. The confusing thing, though, is that the algebra that you end up getting in this subregion, it's not clear how it nests within the larger algebra, right? If you want to prove something like a generalized second law, for example, which states that the entropy increases, you want to compare a number that you got in some subregion of the spacetime to the number that you get in a bigger region. But if you, in regular quantum field theory, algebras nest within each other, and therefore you can compare the numbers that you get from individual calculations. But in this case, because everything is kind of gravitationally addressed to infinity, there's no similar nesting that you get of these algebras, and so it's really what's unclear is how to compare the formulas.
But even if you don't compare, do you know if it's type 2?
Yeah, I think in the case where you have a killing horizon, I'm not sure.
This is the usual thermal argument.
Yeah. So I think, if you restrict. I think what you can get away with is the fact that when you cut this horizon, the state is, and you restrict to this state to the future of. Maybe I should work on the past here. If you restrict the state to a subregion, to half of this horizon here, I think you could use the fact that the modular Hamiltonian associated. Yeah, I'm not sure. I shouldn't try to guess this off the top of my head. I don't know if it's type 2. I think my comments were basically in the direction of if you could determine that it was type 2, it's not even clear how to even compare the formulas that you would end up getting. But you're correct that at the top of my head, I'm not even sure it's type 2.
Really basic question. So before this talk, if you said generalized entropy of a black hole, I would imagine that's the area plus the von Neumann entropy of the quantum fields. So where's that second part in your formulas?
It's all there because the formula is generalized entropy. So the point is that you get the whole quantity in the calculation. You don't get the individually diverging terms, right? You can split the term. Let's see if I can go back. So the claim is that the von Neumann entropy of the quantum fields of the gravitationally dressed quantum state, so this is now the state with this extra mode of the gravitational field, is equal to the full generalized entropy.
Okay.
Right? So this thing hides the area over 4g Newton, which is diverging as g Newton goes to 0, as well as the von Neumann entropy of the quantum field in the exterior. Both are ill-defined, but their sum is supposed to be better defined, right? So that's what you get out from the calculation is the sum of the two quantities. Yeah, it is a little confusing because I'm computing a von Neumann entropy of a well-defined thing, right? Like this is some number, and the number is equal to the generalized entropy.
Sorry, another question. So does this all hold if you still have non-minimal coupling to your matter?
This I'm not sure.
Shouldn't that be covered by discussion of
Yes, you're right. Thank you. Yeah, this would be covered by that. Yeah, I mentioned before that this is valid for any diffeomorphism covariant Lagrangian. That's the case that Bob considered when he was doing the walled entropy. So I'm assuming that's the case that you're considering.